Many globebusters, or people who don't believe the spherical Earth model, like the idea of a flat Earth because they observe the horizon to be flat. In this video, I will try to answer the more and more fascinating question: should we see the curvature of our planet? The short answer is yes, we should. And we do see it, it's just that we don't really notice it. Here is a picture of the horizon, and indeed it does appear flat on a first glance. But let's face it, it is difficult to be sure since the field of view is so wide. Luckily, we can make it narrower, which is equivalent to gaining a more distant perspective. Now, the curvature is easily observed. There are two key points that need to be noted here. One, the picture was taken with a rectilinear lens, so there are none of the fisheye curving effects. And two, the horizon line is below the center of the lens, so the fisheye effect would have curved the horizon the other way around, much like it happens in the following picture, where a conventional lens was used. Now you can easily see what the horizon looks like through a non-rectilinear lens. So the next time you claim the photos of Earth from the International Space Station show the curvature because of fisheye lenses, bear in mind, it could also look like this. Now, a slightly more advanced question. How should the horizon appear as a function of height from the planet's surface? To answer this, we must first understand our field of view. We have about 120 degrees horizontal viewing angle and 100 degrees vertical, and hence we can approximate the rectangular field of view with the width to height ratio of about 1.45. The maximum viewing distance and its dependence to the height off the ground can be calculated by employing this rather simple geometric model. We draw the tangent to the circle from point A, where we are, and knowing that it will be perpendicular to the radius at point B, we can find the distance by using Pythagoras' theorem. However, when applying this model to the real world, we must also consider atmospheric absorption. On the clearest of days, we will see at most 150 kilometers, which corresponds to a height of 2,000 meters. This limitation also causes problems for the previously described rectangular field of view, which now becomes similar to the inside surface of a spoon. This will of course make it even more difficult to notice the curvature, but for the sake of simplicity, we will continue with the rectangular case. With this in mind, I designed a simple simulation to illustrate what the curvature of the horizon would look like as a function of height. Considering the human field of view, I was able to apply a constraint on the plot axes to resemble what a person would see. Here we have the results for several heights, with the latter being the idealized maximum viewing distance, which is also more or less the distance you'd see from the window of a plane. One key observation here is that even though we are in a very idealized model, it is still quite the challenge to notice the curvature. Let's now apply the same horizontal shrinking treatment, as we did with the pictures. So why is this true? Well, because Earth is massive. Maybe this will paint the picture better. If we rescale it to a 1 meter exercise ball, then an average person of 1.7 meters becomes 130 nanometers, or the size of the HIV. Not only you would not see this, it is beyond the detection of an optical microscope. If we consider a plane in our rescale analogy, the 10-kilometer height becomes 0.78 millimeters, so less than 1 millimeter away from the surface. Yes, that's how close to the surface everything happens, and why it's not so trivial to observe the curvature.